All right, so let's talk about time integration. So we found our dynamic equilibrium equation. We know how to get from the governing differential equation all the way to the algebraic equation that we need to solve, but then we could not solve it, right? We have one equation. I have in this equation displacement, velocity, and acceleration. So in a way, I have three unknowns. Of course, they are related to each other, but I still have three unknowns. So I have to add two other equations in order to solve for these quantities. Notice that now, for the first time, I'm going to introduce the damping. We're going to do Rayleigh damping, which is viscous damping that is proportional to a linear combination of mass and stiffness, where this mu and lambda are just simply some constants. So this is a way you can introduce damping into the system. And now, well, we're going to discuss these two equations here. Some people call this a beta-gamma method. It's actually Newmark's family of methods. And it is indeed a family of methods and not only one method, because depending on your choices of beta and gamma parameters, you obtain a concrete method that perhaps was published earlier by someone else. Indeed, Newmark was really a generalization of different time integrators that led to different approaches, right? And we're going to discuss the choices and what are the benefits of choosing one over another, because each one of these are different in terms of stability and accuracy. So you may choose one set of parameters that eventually blows up your displacements, grow unbounded, so they are not stable. So in order to have stability, you need to decrease the time step. And so there are some methods that are not constrained by this. There are methods that are unconditionally stable. And so we're going to also discuss accuracy in general. If you choose a parameter gamma that is 1/2, you have double order accuracy, so second order accuracy. If not, you reduce accuracy to first order. That means that, well, if you reduce the time step by half, then you also reduce the error by half. But if you get second order accuracy, well, if you reduce the time step by half, then you reduce the error by 4. So that's better. So you obviously want something that is second order accurate. And so again, it's a family of methods depending on the choice of beta and gamma parameters that you choose. Now, how do you get these equations? And again, we're going to spend some time delving into why these two expressions for the velocity and the displacement look like this, right? So we start with Taylor series. So we're going to delve into the theory. We're going to try to get those two equations somehow. So you can write Taylor series like this. You can write the function at Tn plus delta t, so at the next time step in your simulation, as a function evaluated at time n. Everybody knows Taylor series. I mean, I'm just writing here because maybe you have not seen the Taylor series expansion in this complete form, where you also have a reminder term like that, right? And we write it like that because we're going to actually be using the remainder in the definition of our displacement and velocity fields in a minute. Okay, so we take the Taylor series expansion of the velocity, for which we're going to choose s equals 0. So basically, the remainder is going to be evaluated at s equals 0. That's why this whole thing here, when you to the power of 0, is going to be equal to 1. And so you have only this term popping up there. And then we pick the velocity for which we have s equal to 1. So again, you see that because you have s equal to 1, we keep the second term as well. And now the remainder is different. It contains this guy here, where I have replaced Tn plus delta t by just t at n plus 1. So it's at the following time step. And then we have two expressions that are integral expressions containing the remainders, right, of the velocity and the displacement at times n plus 1. All right? Well, we express the acceleration in the time interval as a function of the acceleration at the endpoints of the interval, right? And again, we can write it down in the same way using a Taylor series expansion like this. And we're going to be multiplying one of these expressions by 1 minus gamma and the other one by gamma. And then we add up, right? And then we obtain this equation I'm going fast because it's just simply manipulation. I'm just describing what the theory is doing to obtain those two expressions in the beginning. We take now, again, the expression, and then we multiply by 1 minus 2 beta and by 2 beta to get that expression. And now we have these two equations, 38 and 39, that are actually describing the function of the acceleration within the interval. That's why tau is within the interval, right? Not at the endpoints, right? And then, well, we know that the reminders have of certain order. We don't really care much about that. But then, with that expression of the acceleration inside the interval as a function of tau, then we can plug that back into the remainder expression that we had initially, right? And we get these two equations here for the, if you remember, one was for the displacement and the other one was for the velocity, right? And so we get these two expressions where Rn, as you see at the end, is again remainder with some order of accuracy. But these are the expressions that we're going to put back into these guys, right? So now we have a concrete equation for what I'm going to replace this and this with, right? So when I take this and I plug that back, again, substituting equation 1435, we get the following approximation for the Numerical method, and this is essentially the way you get those two expressions. And of course, there is a lot of manipulation. You can go slowly, you can check, double check, triple check. This is the actual math to get to those two expressions. But now that we have an equation for the displacement at n plus 1, and I have an equation for the velocity at n plus 1, combined with the dynamical equilibrium equation that has displacement, velocity, and acceleration, now we have three equations with three unknowns, okay? When you plug that back, right, you can reorganize terms here and there. And what you're going to find is that there are some terms here, for instance, on your left-hand side, that are going to be basically some sort of, you could argue this is some sort of equivalent mass matrix, right? It's multiplying the acceleration, right? And then you have the, in a way, on the right-hand side, the force, then you have some terms. And if you notice, there are some terms that are just a function of the previous time step that are known already because you have already obtained the solution up to that point. Now, there are some terms that are only a function of the end of the interval at n plus 1, okay? So this is going to lead to different approaches, again, depending on the value of gamma and beta, and some are going to lead to implicit time integration strategies, also explicit time integration strategies. You know the difference between those? Explicit are those that
are conditionally stable.
Nope. What is the difference between explicit and implicit?
Explicit entirely depends on the previous time.
Yes, an explicit time integration scheme, you can obtain the solution at n plus 1 solely looking at quantities that were obtained at the previous time step. Whereas an implicit time scheme, in order to obtain the solution at n plus 1, you also need to look at quantities at n plus 1. Therefore, you cannot just simply march in time, right, by just simply solving in time as in explicit, but you need some sort of iterative scheme until you get to converge so that the left-hand side in this expression is equal to the right-hand side in this expression. So those are implicit time integration schemes. Yeah? So we talk about consistency when we say, well, a method is called consistent as long as you can guarantee that as your delta t, or the time step that you choose, goes to 0, right? Both the acceleration and the velocity at the ends of the interval get close to each other. That is simply, it makes sense. You wouldn't want something that does not behave like that. So that is the concept of consistency, right? It makes sense that as we're making the time steps smaller and smaller and smaller, obviously these two things have to be equal to each other, obviously also at the limit. Remember, I'm taking the limit as the time step goes to 0, right? Those two quantities have to be equal to each other. The stability is something different, right? We don't want a method that blows up. So the method has to be stable. Blows up means that displacement grows unbounded, for instance, right? Or this starts oscillating and it oscillates more and more over time. This makes no sense. There are methods that are unstable. So here I wrote, an integration scheme is said to be stable if there exists an integration step delta t naught greater than 0, so that for any delta t within 0 and delta t naught, a finite variation of the displacements or velocities at time tn induces only a non-increasing variation of displacement and velocities calculated at a subsequent instant tn plus j. In essence, all I'm saying here is like the method has to be stable, meaning that it's not going to blow out of proportions. The displacement is not going to grow unbounded. Same with velocities and accelerations. So with these two things, let's look at what are the different options that you have in numeric family of methods. So in order to look at the different concrete methodologies, we look at two things. One is amplitude error, right? So if, let's say you have free vibration and you want to, and you have no damping, well, you know that your amplitude should not decay or increase over time, right? So we're going to define AH divided by A, the numerical amplitude ratio. So AH is the one that is produced by the computation. A is, let's say, your analytical value of the amplitude. Obviously, you want, if you don't have any damping, you want that to remain 1. So the error is essentially everything that is different than this quantity here. So error would be 0 if this is equal to 1. Otherwise, you do have some error in the amplitudes. And we also look at the periodicity error. So if you look at something vibrating freely and you have, let's say, an exact representation of how that should behave, well, you don't want the period to be elongated or shortened, right? You want to keep that period. And so if I call delta t the difference between the computed period of my vibration with respect to the exact analytical period, then that delta t is going to give me also some measure of the error. Right? So I'm looking also at the periodicity error. Well, this table here summarizes a bunch of different methods depending on the value of gamma and beta. Remember, gamma 1/2 was second order accurate. We want that, right? We want second order accuracy because we know that as we reduce the time step, the error to obtain the dynamic solution is going to reduce faster. So we do want second order accuracy. But depending on the value of beta, we have different techniques here, different approaches. So the central difference, everybody knows the central difference. Perhaps is the most known explicit time integration scheme. So this one is an explicit time integration, the central difference. Of course, there is a stability limit and it has some error in the periodicity. Notice that there is no amplitude error. Central difference schemes are widely used in many explicit finite element codes. It's widely known. Particularly, I don't like explicit schemes. I don't like them. You could argue, why would you use an explicit scheme? Well, they have a lot of value for certain types of problems. There is the only way to get some solution for certain types of problems, right? So you may say, well, let's think about a very complicated problem, dynamics. Let's say I want to test the frame of this car, how it behaves when it crashes against a wall, which is something that is called crash worthiness, and it's widely done in research and development in all these fancy car manufacturers, right? Do you imagine how extremely difficult it is to model that problem? Who can give me some examples of the complexity that involves crashing something into a wall?
You have material nonlinearity.
You have material nonlinearity, you have plasticity. You have what else?
Contact nonlinearity.
Contact nonlinearity.
Fracture.
You have fracture.
Your crash is not like a steady state excitation.
It's not a steady state. Of course, there has a huh? Yeah, you have to capture all that. It's impossible. It's nearly impossible. So many people use explicit. Now, I argue, is that of any value? Like you see the solution was obtained by an explicit formulation, but there are so many different types of nonlinearities in the problem that you just obtain a solution and you're like, is this really what is happening? Well, I have a good argument, right? Probably not, but then we check, right? We can reduce the time step. We can make sure that the energy lost, because many of these techniques are not conserving energy, the energy loss is so small, right? Because I kind of reduce the time step so much that I can guarantee that, let's say, the moment I enter in contact with the wall, I kind of conserve the energy or most of the energy. Otherwise, it's just getting garbage. So you have to be very careful when you are dealing with explicit integration schemes, right? I particularly like implicit integration schemes because we do have some convergence, right? So in order for me to get the solution of the system at n+1, I need to iterate. And until I don't get that equation satisfied, I am not done iterating. But when I converge, I can guarantee that the solution at n+1 is going to be the right solution. Now, is this easy? It's super hard. Why is hard? Again, because of the reasons you just said, right? There are many types of nonlinearities. Just looking at one type of nonlinearity, if you look at material nonlinearity, well, it is not so straightforward to obtain the solution using Newton-Raphson so that it converges nicely, quadratically. You need a properly derived, consistent tangent matrix, and sometimes that is hard to do. At fracture, good luck. At contact, contact is the worst of the nonlinearities out there. In fact, every nonlinear finite element package you see out there performs very nicely for material nonlinearity, but try to solve for contact. Good luck. Unless contact is very simple and you can use some very simplified node-to-node contact strategies, yeah, you may get a nice solution in the contact. Try to use impact. Forget about it. It's crazy. You have energy conservation. I'm not so sure. And then if you don't have, let's say you have sliding and now you don't have node-to-node anymore, and then you have node-to-element or what is called node-to-segment or segment-to-segment contact, and try to get proper transfer of tractions or a numerical scheme that does not produce oscillations of the contact traction. It's a nasty problem. Nasty. So implicit schemes are also not very easy to work with, right? So that's why also people, at least they use an explicit scheme and they get something and they are happy with what they see and they go, okay, that's what it is. Okay, so but again, I'm talking about all of this because even if you choose an explicit scheme, you have to be careful and you have to be very critical about the results that you get, particularly if you are dealing with nonlinearities in your problem. Imagine you are predicting at time n, what your solution is going to be at n+1. So all sort of crazy stuff can happen between these two time steps, right? Contact, material nonlinearity, and still I'm predicting what's going to happen. So, but luckily enough, the sector difference is not the only scheme. And then here in the table, you have some other different type of concrete methods that result from the Newmark's family of methods. You have Fox and Goodwin linear acceleration, the average constant acceleration, which perhaps in my opinion is the one that I like the most. Is the trapezoidal rule. For those of you who have heard about the trapezoidal rule, this is the average constant acceleration. And in the end, I also wrote the modified average constant acceleration method. And the idea of that modified method is essentially that you can introduce some sort of damping into your system, numerical damping. So in essence, if you want to dampen high frequencies in your simulation, and you want those high frequencies to die out as you obtain the dynamic equilibrium, as you solve the dynamic equilibrium equations, you can introduce some damping that way with a modified average acceleration, constant acceleration method, okay? And here in the table, we have tabulated everything that is insofar stability, amplitude error, and periodicity error. You see that when you see an infinity here, that is unconditionally stable. So you can pick any time step that you want, and you're going to get an accurate result. In reality, we want to see the dynamic response with enough accuracy so that if you have high frequencies, you don't jump from here to there, losing all that information, right? So in a way, you really want to choose a time step that allows you to obtain the solution at the level of precision as your highest frequency in your response, okay? Or maybe not. Maybe you just want to get rid of all that high frequency content and then you just obtain whatever main. Yeah, you tell me?
The modified is it the same as the alpha method?
Alpha method is different. The HHT method of Hilbert, Hughes, and Taylor, it's a different method. But the HHT method can also, or the generalized alpha method is called, right? Like you can also introduce damping for high frequencies.
No.
Yeah, but it's not the same. So yeah, you have a question there.
Yeah, I'm wondering because all of these, the way I understand it, it's the same effort to implement them. You get the same equation, and then when gamma and theta shows up,
Yeah.
you
Plug one or the other. Yeah.
So do they have separate types of problems that one is more applicable for than the other? Why would you pick Fox and Goodwin as opposed to average constants?
That's always been my question. Why we pick this or that? In reality, the times in my group where we had to pick a method, we went for the one that we knew was working the best, and then we just kept to that until you face issues and you find that there are some problems with the method. Like for instance, we have done some work in dynamic fracture propagation, right? And we tried the Newmark family and we tried trapezoidal rule, and we see that when we are propagating a crack in the dynamic setting and we have inertial effects, we're using a very fancy enriched formulation, we get oscillations in our so-called dynamic stress intensity factors. So our Newmark approach to this problem was not good enough. So we started to look into different methods. And none of the Newmark family approaches actually solve the problem. And we tried Bates method. I will talk a little bit about that approach. And that also didn't solve a problem. So actually we have an open question we cannot resolve because we don't have a proper time integration scheme to deal with the issue of fracture propagation using enriched finite element methods, which is very, very annoying. And it's been in the back of my head already for 5 years. But to answer your question, you pick a method that works until it doesn't, and then you move to try something else. But in terms of implementation, yeah, it is the same effort. I would argue that for all implicit methods, it's the same implementation. If you have an explicit approach, you choose for a simpler implementation, right? Okay, so some remarks about Newmark's family of methods. Yeah, we're in good time. Fox-Goodwin method has very favorable phase accuracy and no leading order amplitude error, but is conditionally stable. Well, you can see that from looking just at the table. The average constant acceleration method is unconditionally stable for linear problems, second order accurate, and has no numerical damping. This is the one that I have used in the past. My students have used this. And it's a so-called trapezoidal rule. It works great, again, until it doesn't, and then you have to figure out what else you can choose. I don't know why I have an extra bullet there. That's a mistake. The modified constant average acceleration scheme is an unconditionally stable scheme that introduces numerical damping to modes of higher frequencies in the model. Of course, that is going to depend on this value of alpha that you choose. Remember that you have second order accuracy as long as gamma is equal to 1/2. The moment you add something, yeah, you are not there anymore, but at least you introduce numerical damping to your scheme. And then for the average constant acceleration method, or the trapezoidal rule, which is gamma 1/2, beta 1/4, and we discussed this already, right? You can choose any time step, but again, you really want to resolve, let's say, the response up to the highest frequency that you are interested in. Right, so if you say, of course, any dynamical system is going to, in the end, the response is going to be determined by a combination of different modes, right? If you want to capture high order modes, yeah, you want to be able to reflect that in the time step that you choose. So normally, you basically have this rule of thumb, right? You choose a time step that is the period of your high frequency divided by 4, and then you can at least capture that higher frequency. All right. In terms of implementation, we also talk a little bit about this. There are different ways to implement Newmark family of methods in a finite element software. Normally, what people do is they implement this in a predictor corrector type of approach, where you basically predict. You have a predictor phase where you predict what is going to be the results of your displacement and your velocity at the end of the interval, and then you completely neglect the effect of the acceleration at that stage in the computation. After you obtain the acceleration, then you modify or you correct those predictions in order to get the actual values at the end. So that is a predictor corrector. Of course, keep in mind that, again, if you are dealing with an implicit time integrator, then you're going to have to converge up to certain tolerance so that this holds. And so this is normally the way it is implemented. Of course, this is very simplistic way, and I'll give you also references to where you can find more information about how to properly implement this in a computer. Our implementation was taken from the book of Tom Hughes, who is also one of the gurus out there of finite element methods, and it works remarkably well. And just to finish all this information on time integrators, I actually like a very simple example that was discussed in a paper by Bate. Well, of course, he was promoting his approach, right? He has his own time integrator that happens to be, for certain types of problems, better than pretty much every other Newmark method out there. So he's looking at this very simple 3-degree of freedom system, where it just happens that there is a very, very, very high stiffness here. So you can expect to have something that has high frequency content in your simulation, right? It's very high frequency. Remember that the frequency is proportional to the square root of the stiffness, right? So for a 1 degree of freedom system, the frequency is equal to the square root of stiffness over mass. So if this K1 is extremely high and is basically connected through another spring with a K2 equals to 1, there are orders of magnitude difference. So, well, this is one case for which his approach was able to outperform all the methods in the Newmark family of methods. And of course, you can find more information in this paper at the bottom by Bate and No. So the idea is that, well, he looks at that problem and then he says, well, I'm going to try the different time integrator from Newmark, and then I'm going to write my own method, and I'm going to call it Bate method. So that's why we like to call things in certain ways. I don't have anything named after me so far, but I have named some methods out there that are not called Aragon, but they're called discontinuity enriched finite element. Maybe someday one will say, well, this is Aragon's method. I will be happy. But no, Bate decides to do it up front, like the method, like boom, in the paper, this is my method. Well, the guy is extremely smart, and he has done so many nice contributions to the computational mechanics community. So I will grant him this. Let's call this the Bate's method. It's a nice idea. So he looks at the displacement at the end node for various methods, and you have a reference solution for this problem. And so you have Bate's approach, of course, for the displacement at the last node. Remember, I'm looking at this node here. For the displacement there, everything seems okay. And then for the middle node, everything seems to be okay. But then when you start looking at the velocities of the different methods at the different nodes, suddenly you have that at that middle node that is connected between a very, very high spring stiffness and a very low spring stiffness, you get some things that start to go crazy, right? So you have, in the velocity, you have crazy oscillations by the trapezoidal rule, which is the one that I advocated a few minutes ago. In other words, if you have high frequency content, maybe the trapezoidal rule is not the right thing to choose. Going back to the question of the gentleman here, what method you choose? Well, you choose something that works, and then if you see something like this, you should say, well, something is really, really going wrong here. And so, but Bate's method is like spot on, right? And if you look at the acceleration, it's even worse.
Have you tried this method for your fracture propagation?
Yes, I did try this method for my fracture, and it doesn't work. or maybe the student didn't manage to make it work. I don't know. I had cases where in my head I have this idea, and I'm like, this should work. And I'm convinced that it should work. I just don't have the time to do it. So you get a student to work on the problem, and after, let's say, 1 year of a master's, it doesn't work. And I'm like, but it should work. and then a PhD student of mine comes, and she's like, yeah, but why this guy didn't do it this way? And she's like, yeah, she has a point. Yeah, so how about we do it that way? And then her first paper was basically the correction of that, and she made it work. Yeah, so I don't know if some of you may know Sane. Sane was my PhD student. She ended up earning the Biezeno Award in the Engineering Mechanics School for her work on enriched finite element methods. And she actually, with one comment, corrected 1 year of work of this master student. So yeah, sometimes you have this thought, something may work. And I don't have a solution to the fracture problem. I do have some idea how to fix it. But yeah, it's still, actually, I recall that even Ted Velisco, you know who Ted Velisco is? Ted Velisco is, he was a professor at Northwestern University. He's the one who started promoting XFEM. XFEM is the extended finite element method, which is basically a generalized finite element method applied to discontinuities. All of this I'm talking about, you can find it also in my book. I'll share the book with you guys if you are interested. It's a crazy story, but just to make it short, Ted Velisco was a professor at Northwestern University. He died already, but he was very famous. He was the editor-in-chief of a very famous journal called International Journal for Numerical Methods in Engineering, IJNME. Well, it turns out that at some point, he says, whoever is able to provide a time integration scheme to deal with dynamic fracture propagation in enriched methods, I just will grant a PhD to this person. I will grant a PhD. So that's what he said once. Yeah, he's dead now, so he's not going to grant anything, even if we find a solution to that. Anyways, going back to the time integration story, right? You see here that in this very simple 3 degree of freedom system, you have this acceleration of the second node exploding. Yeah, seems to be something very funny over there.
I like your storytelling.
Yeah, well, I should have more storytelling in my teaching. Sometimes I go crazy. Anyways, finishing, further reading. I'm going to give you some things to read if you're more interested in all of this time integration. You have the HHT approach, the alpha method, right? Or generalized alpha method. So it's another way to introduce damping without degrading the order of accuracy. Bate and No proposed the method that I showed you earlier. And then an excellent book, really excellent book by learning about finite elements and also about dynamics is the book of Tom Hughes. The finite element book of Tom Hughes is really an incredible resource, and in fact inspired some of my work and the way I write things myself in my papers and my book is also largely inspired by the work of Tom Hughes. He is the one who proposed isogeometric analysis, for those of you who know what IGA is. And not only isogeometric analysis, he's also the one behind the Petrov-Galerkin approach to solve for fluids in finite elements, and many other great contributions to our computational mechanics community. And his book is really a masterpiece. And I'm very sad because once I saw him when he went to Illinois. I did my PhD studies in Illinois at UIUC. And then he came to give a seminar, and I had my book, and I asked him, "Can you sign this for me?" And he "What's your name?" "Alejandro." And he signed, and I lost it. Anyways, this is my book. If you're interested in learning about the world of enriched finite element methods, and in fact, most of what I explained earlier in terms of finite element, the definition or how do we get to the discrete equations starting from our strong form, I explain very, very carefully in chapter 2 of this book. In fact, some of the material that I share with you in the slides is also inspired by chapter 2 of the book. Of course, the book is not 2 chapters. So we talk about all sorts of these different crazy formulations in the book, HFEM, PFEM, GFEM, and my own methods that I've been advocating over the years, these discontinuity and rich approaches to solve for problems with weak and strong discontinuities for fracture problems. I have a method for contact as well that I'm trying to continue to develop. And so many of those things are in this book. It should be free for all of you. So please grab your digital copy. Yeah, because I think every copy buys me a coffee or something. So just because of that. Anyways, some further references here for the things that I shared with you earlier. And that's it. This is what I shared with you in terms of numerical methods for dynamics. So I hope you enjoy the material. Again, I recorded all of these sessions, so if you want to hear again the storytelling and read again, you are welcome to do so. I'll probably post this also online in my YouTube channel and in my website. So if anything, I would be happy to share more stories or to discuss anything. If you have a problem with finite element analysis that you may not have an answer for, we can also discuss that. In fact, I recently published a paper with Purilla. He was a PhD student who took another of my engineering mechanics courses on the nonlinear mechanics course, and then we published a paper together using this enriched approach. So you never know what can lead from these teaching sessions. Are there any questions at this point?
I have a question about you said the difficulty to make sure you make things right.
Yeah.
Right? Especially recently, I meet a system I suspect is a chaotic dynamic system.
Mm-hmm.
So then, when I keep enrich the number of degrees of freedom, I keep see things different or a little bit different. Then, if you or me, how do you guarantee what you get is something meaningful or
Yeah.
right?
Right.
Yeah. What will you check?
What will you check? Well, something I teach in my finite element course is that you need, if you see something that doesn't work, if you see some weird chaotic behavior, we just apply in a way common sense, right? What is the simplest problem that you can that has the same behavior? So you have to reduce the complexity of your problem, because if the simulation is already way too complex, it is extremely hard to find out what is wrong or where you have done something wrong. So maybe your system is chaotic by definition. There are chaotic dynamical systems, obviously, but maybe it is not. And whatever you see is a result of a bug or something that you did wrong. You did something in the implementation. You have assumptions that do not hold for your case. So again, try to fall back and try to simplify that problem as much as you possibly can. And if you find a very, very simple case that shows the same behavior, you are more likely to find out what the problem is. So that would be my advice to that. Yeah? It may be still chaotic, but at least you can, remove some problems when you simplify it. Any other questions? Yeah?
Would you or would you not use Runge-Kutta method, the advanced ones, 45 ones, to solve the matrix equation?
Sure. I shared with you one approach to do time integration. These are definitely not the only ones. There are other ways to solve for the dynamic equilibrium equations. I showed this because I'm familiar with this. We implemented this, and for mechanical systems, they work great. And you can also add nonlinearities to this, material nonlinearity, contact nonlinearity, and then you still have implicit schemes that you need to iterate, but they still work. But you can choose anything. Again, going back to the question, there is no fail-proof approach in mechanics. You go for the hammer that works for that nail, and if it doesn't, then you change to a drill, right? You choose another method. Yeah? Well, you're gonna drill a nail, but you see my point. Anything else?
out of curiosity,
Yeah.
do people like also do like stochastic time integration for finite element methods, or is that not?
Stochastic finite elements.
Yeah.
Yeah, of course, everything we have described so far is deterministic, right? But you can bring stochastic approaches. You can say that now my Young's modulus is not just a constant, but it's a function that has a probabilistic distribution, Gaussian distribution, and of course there are ways to incorporate this now. Of course, then you get a response that is within some interval of confidence. So this is something that it's widely studied. It's done. So yes, sure, there are ways to do that. You can go really deep down the rabbit hole in terms of stochastic, and you already know, of course, the work you guys are doing in dynamics with noise. It cannot get more difficult than that, right? If you can quantify and noise and so it can be done in finite element analysis as well. All right, let me stop then the recording, and then we continue talking if anything.